All right. I think it says I before E. Yeah, we got it. Okay. Piecewise functions. And that's what we worked on with the trig class. Oh, look at that. All right, let's go over here. Let's find the website 261. Here we go. What are we looking for? Okay, the new library. Oh, and I did put under supplementary material that the factoring review and the factoring review video, some of these things. I think I did send that to you guys. I might even put the circular function review there too. But okay, limits and continuity. So I've been busy here working with some of these things for you guys. And I have been assigning some of those, even though we've been working on them. They're all designed to get you to be ready for the textbook work that's there. And so let's look at limits of piecewise functions. Let's look at some details here with these. There we go. I want to import that. Yes. Okay. So really the key, if we can add to existing notes, the key to piecewise functions, ladies and gentlemen, we're looking at limits now, but I'm going to do a couple of things here for that, right? Yes, we are looking at limits. We want to evaluate a limit. And so this is why I put the notation there. It's the limit as x goes to infinity, or a, of a function. And then what is the key for this? Because this is your general approach for a limit. But probably we're going to see the left-handed approach and the right-handed approach. You want them both to equal the same value. And really, ideally, you want them both to equal what? A finite value L. L is a nice finite number, okay? So you really have the left and the right. If they're the same finite value L, well then guess what, ladies and gentlemen? We can say that we can evaluate the limit as x goes to a, okay? Now, what's the key here? The key is really, you got to be able to read the function and understand which pieces of the functions are associated with the left side of the value a and the right side of the value a. So in other words, you have to know how to read this, is what I'm saying is the key. How do you read a piecewise function? And then if you know how to read it, you can very simply evaluate it, and I'll show you what I mean. So, okay, let's go take a look at this first one. So here's my function. Here's what I mean. You have to be able to evaluate it, right? This is a piecewise function. It's a function that's defined in terms of pieces. And I'm going to say in terms of pieces, like pieces that are to the left of a value a and to the right of a value a. So in this example, I want you guys to read that you have, what's the function here? I guess you have what, x squared, and you use that piece for x greater than or equal to 0. Okay? And then you use what piece? The bottom piece for x less than 0. So I just see this as, okay, we got the top piece and we got the what? Bottom piece, okay? They're defining that around the value what? 0. That's a key idea too. All right. So that's kind of like the cutoff point. Now let's look at the graph, okay? The graph should show a parabola for values of x that are what? That are greater than or equal to 0. Those values are to the right of 0. Would you guys agree with me on that? So those are to the right of what? Right of 0. And the green values of x here, these are all what? This is to the left of 0. So we do have to really understand what we're looking at. Okay? So far, so good. Values that are bigger than 0 are to the right. Values that are less are to the left. Now, let's see if we can read this here. I want to kind of remark here about this here. Can you tell me what's the value of the function at 0? What is f of 0? Just by reading the pieces. Anybody know? That's what? 0 to the second power, which is what? 0. Now, this is functional evaluation. So f of 0 is 0 because, what are they saying? Use x squared when x is greater than or equal to 0. That's what you guys use. Now, okay. Now, this is why you have a dot here. See that dot? That dot is saying that's the location of 0, 0. You see this open dot? What's the address of that open dot? That is 0, comma, -3. That's not on the curve, okay? That's not there because they're saying you use x minus 3 when x is strictly smaller than 0. So reading your function is extremely important for you to do the work in calculus. Did you guys see piecewise functions in pre-calculus? Do you guys know what I'm saying? You should have. So, okay, good. So far, this isn't even calculus yet until they say what? How do you find the limit as x goes to 0 from the right of the function now? It's not so hard to do. What do you guys have to know about this limit approach? If it's plus, it's to the right of 0. What values are to the right of 0? X values that are bigger than what? 0. Okay. Then how do I evaluate this limit? Well, these values are bigger than 0, aren't they? A limit is an approach. So which piece do I have to use for values of x that are bigger than 0? X squared, is that true? It tells you. Okay. So then I know, oh, that's 0 squared. The book calls this by what? The book will say by direct substitution. And what is 0 squared? That is 0. So take a look, ladies and gentlemen. That's the calculus part now. It's a limit question. And that's a right-handed limit because you're approaching 0 from the what? Compare that to the next question, and you're approaching 0 from the what? Okay, if you approach 0 from the left, what do you guys notice about your values of x? They have to be negative. Is that right? Okay, now, so what piece do I use now for negative values of x? X minus 3. So you're going to plug in by direct substitution 0 minus 3, which equals what? -3. So ladies and gentlemen, these are the kind of things you're going to be doing on your first test. I highly recommend, and I know what people do, is people do things backwards. And if you do things backwards, you get backwards results. And you go, what are you talking about? You go, hey, Mr. Judge, can you send me that study guide now? And I usually say, because I get that from trig students too and statistics students, I say, do your homework. No, I just want to see the study guide first, and then I'll try to do my homework. And I think that is such a very bad approach. That means you haven't done anything. And if you haven't done anything and you expect to study the night before and it's going to work out, you're going to learn the hard way. It doesn't work that way. So I recommend doing what I ask you to do every day. Try to come through the front door. Don't try to sneak through the back hoping the window's open, because it's going to be closed. You're going to see what I'm talking about. You guys are going to become true believers. You're going to be like, oh my God, Mr. Judge, you're so right. So do your homework. My life didn't change, and so I started doing my homework every day. Then everything changed for me. So try it that way. If you want to do it the other way, then you might say, I've been doing it this way my whole life. And I'll remind you, has it worked out? Has it really worked out for you your whole life? Maybe, maybe not. But like in a college environment, that won't work. But these are the kind of questions you're going to be asked. What do you guys think? Is that easy or is that hard? I think so. But what about this next one? What would you say the answer is here? Anybody know what's this answer? Yes, thank you. Does not exist. Now, what I write on a test is justify your answer. Why is the answer does not exist? Like, you're seeing all the work, ladies and gentlemen. But why is this a does not exist? You know what I'm looking for? This statement. Because the left-handed limit of the function is not equal to the what? Right-handed limit of the function. Okay? That's why it's a does not exist. This is the big Y part. And very simply, it's because 0 is not the same as -3. Okay, you guys okay with that? In fact, they're going to ask you continuity questions. They're going to say this. Is the function f continuous at x equals 0? Justify the answer. Do not guess. Show your work. You don't want to just say yes, no, because you're guessing. You guys see what I'm saying? They want to know, do you know the definition of continuity? What was that definition? I gave that to you. Do you guys remember? Here it is again. If the limit as x goes to a of a function is the same as f of a, which is L, finite number, then f is what? Continuous at x equals a. So I'm going to try to kill two birds with one stone here, because we've actually been working with this definition of continuity really all along. But let's kind of put it together for you guys so you guys can get started and get studying on this kind of stuff, right? So what do you guys know what's happening around 0? Is this function continuous at 0? What would you guys say? F is what? Not continuous, right? At what? At x equals 0. But why? They want us to justify the answer. Does anybody happen to know what that is? Here's the reason. Because the limit as x goes to 0 of this function is not equal to f of what? 0. Here is what they're looking for. Why is that? Do you guys know why? Because the limit is what? Does not exist is not the same thing as saying what? 0. F of 0, we started the lecture on by saying is 0. But what's the limit? Does not exist. This is the reason. They're looking to see, can you use your definitions? Do you know that around 0, what's happening with this function around 0? The function jumps. It jumps from that green portion to the what? To the orange portion. So that happens at 0. It jumps. You guys okay with that? So notice the key is, can you read your what? Your function. That's it. What do you guys think? Is that impossible? Is this kind of like the stuff we've been working with, I think, over and over again? It is. Let's look at another situation. Excuse me. Here's my function. Yes.
I had a question.
Yeah.
Would it be the same saying like as for like that question, like if x approaches 0 to the left is not equal to 0 to the right, as like an explanation, or is I guess like more complicated way of saying it's not equal to f of 0?
Say it again.
Like so you know how we put like limit f of x is not equal to f of 0, like as an explanation.
Right.
Would it be wrong to say it limit f of x as x approaches 0 does not equal because f of x as x approaches from the left is not equal to f of x as it approaches from
I mean, I think it's probably they're literally looking for this statement here. But you're correct that the left-handed limit, in order for a limit to be a finite value L, both left and right have to be the same. But you're certainly correct about that. But if they just ask you, and they will, because I ask the questions, right? Is this function continuous at 0? Don't just say yes or no. Because I always put show your work, justify the answer. Saying f is not continuous at 0, what you're saying is what you're right here symbolically, which is the definition. It is not. It does not satisfy the definition. Don't say it that way. Cite the definition, right? This is the definition. In order for a function to be continuous at a value L, the limit has to equal f of the value of the function at that location. That's really the straightforward justification. You know, that's like that's what they're really looking for as an answer. You know, compare that to this situation, and you might say, okay, what was the key again? Can you read what this says? You got a top piece. Okay, there's a top. And when do you use the top piece? For values of x that are greater than or equal to what? 2. You guys okay with that? That's when you use that top piece. When do you use the bottom piece? And what's the bottom? It's negative x plus 11 is the bottom piece. Okay. For what values of x do you use that? For values that are to the what? That are smaller than 2. Do you guys happen to know what this is code for saying? These values of x are to the right of 2. These are to the left of what? 2. Is that true? That's what they're really saying. It's easy peasy. Now, I want you to note, because on this worksheet I didn't do that, but what's the value of the function at 2? What's the value of that function at 2? Do you guys know what you do to get the answer? You take what? 2 cubed plus 1. Why do I say you take that? Because you use the top piece when x is the value 2. That's how the function's defined. Okay, and then you do some arithmetic and say, oh, 8 plus 1 equals what? 9. There you guys go. All right, and that's actually the location right here. I put the dot. This is 2 comma what? 9. I emphasize that location even. All right, there we go. Okay, now, what do they want to know? What's the limit as x goes to 2 from the right now? Okay, I use what? The top, which will be, by direct substitution, that 2 cubed plus 1, which is 8 plus 1 again. Well, that equals 9. But what's the left-handed limit equal to? Well, what do I do now? I plug in 2 for values of x to the left of 2. So that gives me negative 2 plus 11. And then that also equals what? 9. You guys good with that? Oh my God. So what does that mean if both the left-handed limit equals the right-handed limit? What's the value of that limit going to be? 9. Good.
And then that means that they're continuous, right?
Well, let's write down this question over here. Is f continuous at x equals 2? Just yes or no. You might say, oh, yes. Justify your answer. What do you say? Because the limit as x goes to 2 of the function equals f of what? 2. You see, ladies and gentlemen, the limit value is 9, and the value of the function is also what? 9. How do we know? We found it earlier here, all just by being able to read the statement, the function. They both equal 9. Yes? Whatever they give, whoever writes it, it's up to them. They can have x greater than 2 on top, but then x less than or equal to 2 on bottom. Depends on who's writing it. And I just happen to do that to get people started. You know, because if I start changing it around, it's some people, not everybody might, that's enough to throw people off. And it all comes down to the advice I just said there in the beginning of that worksheet. Can you read this piecewise function? That is it. And you're going to be surprised. There are people that can't read that. And you say, why can't they read it? Well, maybe they never seen it before. They never seen a piecewise function. And that happens, you know. But that's all you have to do. And you cover piecewise in 260. And in fact, you know what an easy way to think of continuity is, really? If you want to think of it poetically, when you draw this curve, did you ever pick up your pencil? And the answer is what? No, we never picked up our pencil. It's continuous everywhere for all real numbers, like nice polynomials and sines and cosines. When you drew this picture, did you ever have to pick up your pencil? The answer is yes. I picked it up here at x is 0, then I put it back down and I continued drawing my curve. So wherever you pick up your pencil on a curve, that point location is where the function is not continuous.
So you could technically figure out whether f is continuous at the given with or without the graph, basically.
Well, you can do it just graphically by looking at it, or you could just use the definition. What happens a lot, like in your book, and even in some of these limit questions, they don't even give you the graph. And then when you talk about continuity, sometimes they do. So sometimes they give it to you, sometimes they don't. So you say, well, Mr. Judge, what if they don't give me the graph? Well, then they expect you to use your definitions. And then sometimes they'll give you a nice graph, and you go, oh, expect you to use what? The graph. So take a look at this one here, ladies and gentlemen. This is also piecewise, but you got to learn how to read this. What's the top piece? It's the constant pi. Pi is a number. And when do you use the top? When x equals 0. You go, okay, that's pretty restrictive. I know. It's how they define the function. So what that even means is f of 0 equals the numerical value of pi. And you say, why? Because they just told you. Use it when x is 0. Okay, and then what do you use? You use the bottom piece when x is not 0. Okay. All right. Bottom. So as a graph, essentially, this is the picture. Yes, this function, 1 over x, is not defined when x is 0. We already know that 1 over x has a vertical asymptote there. But what they did was they now created a function where they defined the value of x at 0. It's pi. Now, what does that even look like? That looks like what you guys see here. Yes, you were expecting to see a vertical asymptote. I know. But what did they just do? They defined the function at 0. And then you go, can they do that? They sure did. They just did right now. Have you guys seen the book questions? Do they look a little bit like that for some of them? Uh-huh. I'm sure they do. How do I know? Because I took them from the book. All right. You guys already know for this function. What's the limit as x goes to 0 from the right? What would you say that is? And you might say, Mr. Judge, how do I know? You know how I say, remember that worksheet I said, hey, these are curves every what? Every B-STEM student should know. I used to call it curves every calculus student should know. Right, yeah, x, you have a vertical asymptote there. You guys remember that curve? This is a 1 over x curve. I recommend you guys know that curve because as x goes to 0 from the right, what do you guys notice? Goes to infinity. As x goes to 0 from the left, what do you notice? Minus infinity. So I know infinity minus infinity. This is what Jaime Escalante taught us to know how to do this stuff. They didn't say, go to your calculator and put x's, 0.0, 0.00000001, figure out what that meant. No. This is why I gave you curves every B-STEM student. Because it is that simple if you know the curve and you can look at the graph. And there's only a few curves you got to look at. And then what does it mean about the limit? Does not exist. Good. That's it. And then let's ask, is the function continuous at x equals 0? What do you guys know? Is that nice and continuous at 0? The answer is no. Why? Because the limit as x goes to 0 of that function does not equal to the value of the function at 0. Does not exist. Is not the same as pi. Okay? That's the justification. And that's what they're looking for. Just that simple. And, remember what I said, poetically speaking, that notice this, when I sketch the curve at 0, don't I have to pick up my pencil and then plot a point and then continue to sketch the curve? That only happens at 0, and that's what they're saying. Function is not continuous at 0. It is continuous everywhere else, though. Ooh, should we go there? Do you guys have this here? Let's see if you're awake. Oh, I don't think I have. Let's add a page. Go back to that question here. Is f continuous at what? At x equals 1. Is it continuous at 1? Ooh, they like to keep you honest. Does anybody know the answer? The answer is what? Yes. Why is it continuous? Yes. They want you to justify your answer. They sometimes say show. Show it's continuous at 1. Well, because what's the limit as x goes to 1 of the function? Does anybody know what that is? That's 1 over 1 what? Squared. Is that true? Which is 1 over 1, which is 1. Let me double check. Is that what that is? It sure is. Oh, 1, not 1 squared. Sorry. I'm thinking of the other function. Isn't the limit equal to 1? Why is that limit equal to 1? Because what piece do I use when x is 1? The bottom piece. And that for that bottom portion there, that's nice and continuous, right? And I don't even have the point on the curve. Yikes. So whatever. All right. And what is f of 1? Well, what piece do you use when x is 1? The bottom portion, which is also what? 1. So the answer is yes, because why? Here's your conclusion. Because the limit as x goes to 1 of the function is the same as 1. That's why. Well, we'll say f of 1. This is why it's a yes. Okay, so they try to keep you honest. What about this one? Oh, just by looking at the curve, where do you think the curve is discontinuous? There's only one point where this curve is discontinuous. Where is it? Yep, when x is -1. Why? I got to pick up my pencil at this location. Oh, I forgot to plot that point, but the point is when x is -1, I got to pick up my pencil. Is that true? Because there's a hole there. Now, could they fill the hole very cleverly? They can. I can show you how, but what you first want to see, you want to do both. Can you look at the picture in the graph and see it's discontinuous at -1? Okay, what about, here's the definition. They're saying, when do I use the top piece? Use the top piece when x is not equal to -1. Use the bottom piece when x equals -1. Top, what else? Bottom. Okay, what do they want to know? What's the limit as x goes to -1 from the right? What does that mean? If you're going to -1 from the right, what does that mean? X is bigger than -1. Is that true? Is that right? Okay. So when x is bigger than -1, which piece do you use? When it's bigger, what do you use? Use the top. Is that true? Uh-oh. Hold on. Oh, yeah. And what's going on here? Oh, something interesting. Okay. So you say, okay, Mr. Judge, this will equal -1 squared minus 1 over what? -1 plus 1. And then you go, okay, that equals 1 minus 1 over 0. That is 0 over 0. What did we learn last week about 0 over 0? This was an indeterminate form. You might say, what do you do in that case? You guys know what you do? Use what? Algebra. Good job. Use algebra where? Here's really what's on top. Did I send you guys any factoring videos? I wonder why. What's x squared minus 1? X plus 1 over what? X minus 1 over x plus 1. What? Did you guys look at that work? Removable disc. Are you going to wait for the study guide and you go, oh, I guess he was serious about factoring? I'll use the next 4 hours to do it because he just sent my study guide 4 hours before the test. Oh, my God. You see my point? Exactly. Okay. Get rid of the x plus 1. What do you guys have left? So you know what the top piece really is? The top piece is really what? X minus 1. So that's your top piece. I had to use some algebra. Okay. All right, x minus 1. All right, there we go. We'll see more of that in our future. So that means we have what? Negative 1 minus 1, which is going to be what? That left-handed limit is negative 2, ladies and gentlemen. And then, is that left-hand limit negative 2? Let me see, sorry. Yeah. I think the curve is wrong, but okay, never mind. We'll have to correct that. It looks okay with me. Looks okay to me. What's the right-handed limit? Yeah, the curve is wrong. You know why? I can share with you guys why. What's the right-handed limit going to be? It's going to be what? It's the same. Is that right? Negative 1 minus 1. What does that equal? It's negative 2. What does that mean about your limit? The limit's negative 2. Okay. So we answered all of those questions here. You know why I know it's wrong?
Because the graph is supposed to be continuous, right?
No. The graph is supposed to be x minus 1. So that means you have you're over here. The line really looks like this. There's your line. But you have a hole at what? Right here. This is where negative 2 is. I can show you in Desmos. So the graph is wrong. So the left-handed limit does equal the right-handed limit. It is negative 2. We can fix the graph. But what's the value of the function at negative 1? Let's see if you guys can read this. F of negative 1. What's that going to be? What is it? 5. So the function's defined. It's what? It's 5. And those are the kind of questions they'll ask you on that test, because they're going to want to even know, hey, what else are they going to ask? Come on, how do you get that? Oh. Yeah. What are they going to ask? Is f continuous at negative 1? What are you guys going to say there? The answer is no. Why or why not? You know why? Because the limit as x goes to negative 1 of the function, what does that equal? That equals negative 2. And what's the value of the function? Negative 2 is not the same as the value what? 5 here. So the limit is negative 2, but the value of the function is what? is 5, and it's because they defined it that way. Okay, you guys okay with that one? Limit's -2, but the value of the function is actually 5. So those are the kind of things they want to test you guys on. What do you guys think is happening with this picture if you just look at it? Remember I said earlier that they could make that function nice and continuous if they wanted to? Here's what I mean. You see this right here? We can simplify that. Is that right? X plus 6 over what? Over. Okay, what happens with x minus 6? It's gone. What's left here? X plus 6. So you might say, well, what's really happening? Well, you have the graph here, but then there's a hole where? The hole is supposed to be over here. However, what did they do at x is 6? You're supposed to have that hole. If you worked with the removable discontinuities, that's what I was talking about. But then what did they do with the bottom portion? So this is really the top. What did they do on the bottom? They actually defined it so that what? They filled the hole here. So they filled the hole on you. Can they do that? They just did. So if you said, okay, the limit as x goes to 6, so that means from the right, x is bigger than 6. How do I read this? We use x plus 6 when x is not equal to 6. Is that right? We use the top piece when x is not equal to 6. Well, x being greater than 6 is not equal to 6. So that'll be 6 plus 6, which is equal to what? The 12. What about down here? Well, x goes to 6 from the left. That's x smaller than 6. What do I use when x is smaller than 6? The same thing. Because we use it when x is not equal to 6. And then, the left-handed limit equals the what? Right-handed limit. They're both 12. Okay. See, are you awake with this? You say, what do you mean? What's the value of the function at 6? Go back and read. Which piece do we use? They say use that piece when x is 6. What does it equal? It equals 12. So, ladies and gentlemen, this is actually the definition of, what do we know? F is continuous at x is what? 6. And you say, why? Because the limit as x goes to 6 of that function will be f of 6. That's why. Easy peasy lemon what? Squeezy. That's the justification. They're all equal to 12. And at 6, what did they do? They just filled that hole because they defined the function that way. So like you guys can see here, yeah, I mean, it's not that hard, but there is detail. And some of the detail, involves a little bit of algebra there. This is a nice one too. What do you guys think? Let's try this one here. Okay. What do you guys do with this? This is going to be, what? This is a top piece. Is that true? When you use the top piece? When x is greater than or equal to -3. Okay, when do you use the bottom piece of 1 over x? When x is smaller than what? -3. We just read this. All right. Yes, the curves are there. All right. Those happen to be what the curves look like. Here's your left piece. Here's your right piece. And at 0, I'm not 0, at -3. Okay. When they say, what's the limit as x goes to -3 from the right, what would you say? Well, what kind of x values are to the right of -3? Values that are what? Bigger than -3? Is that true? What about as x goes to -3 from the left? Values of x that are what? Less than -3. Okay. So let's just be awake. How do I find the values of x that are to the right of -3? It's the top piece. Is that right? So that's going to be what? 1 minus 3 squared. And I'll put it equal to here. 1 minus 9. What does that equal? That limit is -8. Is that right? Okay. Now, what about the values of x that are smaller than -3? Well, what do I use for values of x smaller than -3? So that's 1 over x. So that's going to be 1 over what? -3. Doesn't that equal -1/3? So, ladies and gentlemen, we have what? The left-handed limit and the right-handed limit. It's in this picture. What's the limit as x goes to -3? Does not what? Exist. Why? Because, why is it does not exist? Because the limit as x goes to -3 from the left of the function, right, does not equal that limit as x goes to -3 from the right of the function. Yeah. Okay? That's why it does not exist, because simply stating -1/3 is not the same as -8. And, because that limit does not exist, the function is not continuous at -3. And when you look at this picture, yeah, there's no way I can draw this curve without having to pick up my pencil when x is -3. So I had to pick my pencil up at x is -3. So looking at the picture and doing the, I should say, analysis, ladies and gentlemen, is definitely what? That's what's going on here. All right, you guys okay with that one? All right, well, we got a lot of these. Let me just skip through some of these since I think you have some good ideas. I mean, you could do. Okay. We're going to start here with question 16, I guess. So we have a function where the top function is x cubed plus 2, and we use that for x being greater than or equal to 0. So here's the top function. The bottom function is used for values of x that are less than 0. This is on the bottom. So as we can see with the first question, when x is greater than 0, or I should say as x goes to 0 from the right, they're talking about using positive x values. Because you're going to 0 from the right, all the x values are positive. So for positive x values, we have to use the top function because it's defined for values of x being greater than or equal to 0. So this would be 0 cubed plus 2. We just plug in that value for x into that function here and do our arithmetic. And that's going to become 0 cubed would be 0 plus 2. And then that limit will be simply the value 2. Okay. For 17, x goes to 0 from the right, that means x is actually less than 0. So for values of x that are less than 0, your piecewise function says use the bottom piece. In other words, plug in your x value down here, and now you'll get 2 minus 0. And 2 minus 0 is the value 2. And so since the left-handed limit equals the right-handed limit, they're both 2, we can say that the limit as x goes to 0, irregardless of the direction left or right, is the value 2 because it's the same. So that's what this means here. Both the left and the right are equal to 2. I want to note something here, that the value of the function as well at 0 is found by using the top function because it's defined for values of x that are greater than or equal to 0. So that would be 0 cubed plus 2, which is 0 plus 2, which is going to be 0. So there we go. Sorry, 0 plus 2 is 2. So the value of the function at 0 is equal to 2. And so just looking at this curve, looks like, yes, we can sketch this curve without picking up our pencil anywhere on that point, especially when x is 0. So they didn't ask this question, but we're going to note and say that this function f is continuous at x equals 0. And why? Because the limit as x goes to 0 of the function is the same as the value of the function. In other words, the limit is 2 and the value of the function is 2. So this is how we actually work with this piecewise function. Okay, I know we're just finding limits, but we're looking at this in terms of continuity as well. All right. Let's look at how to read this piecewise function. Now, you have a rational function on top here that's used when x is greater than or equal to -1. However, there's a problem here with this. The denominator could never be 0. So x plus 1 could not equal 0. We'll set it equal to 0, solve for x, and we know x could not be the value -1. So this is going to be actually strictly greater than. We have to throw that value out. So the top piece is used for values of x that are bigger than -1. The bottom piece is used for values of x that are less than -1. So let's kind of indicate this here. And I think there's a little bit more going on. So we have top and we have bottom. If we look further here, we have x squared minus 3x minus 4 over x plus 1. If we simplify this rational, the top is factored as I believe this will be x minus 4 and x plus 1. Yes. So we can get rid of this portion here, and really your top piece is an x minus 4 here. So the top piece is really x minus 4, ladies and gentlemen. Yes. And that's why you'll see the line that you see in the curve here. But again, x could never be -1. So that's going to be very helpful because of the fact that when you try to look at the limit as x goes to -1 from the right and the left here, this means going to -1 from the right means x is bigger than -1. X going to -1 from the left means x will be smaller than negative 1. So we have to know what piece we're going to use for the value of x being negative 1. So bigger than negative 1 is the top piece, which is really x minus 4. So we're going to plug in the negative 1 here for x. For the top, that's negative 1 minus 4, which gives us a negative 5. Okay. Now, as x goes to negative 1 from the left, these values of x are smaller than negative 1. So we're going to use that bottom piece, plugging in x being negative 1 here, and we get negative 1 plus 5 now. And that answer is actually negative 4. Okay. Yeah. So the limit as x goes to negative 1 does not exist because these aren't the same. Pointing this detail out to you guys. And I'm looking at the graph and I'm thinking here, it looks like, is this the correct graph? The top graph of x minus 4 is correct. The bottom graph of x plus 5 is not correct. So, yeah, x plus 5 actually is not correct here. X plus 5, let me get something out here. Get a pencil. The y-intercept, oh, I'm sorry. X minus 4. Yeah, the y-intercept, the top graph, that looks okay for values of x bigger than negative 1. And the x plus 5, yeah, this graph here should go through this point with a positive slope as well. But really, at negative 1, we should have this over here. So this graph is wrong. We're going to have to fix that one here. Just so you know, there's a hole there. Yeah. And that's a positive 4, by the way. So it's pretty late. Found a typo. Apologize for that. Okay, find the typo in the graph. And really that's what it looks like. But I guess the most important thing to note about this is that at negative 1, this curve is not continuous. The value of the function at negative 1 is undefined. There is no point you can use here for that. Negative 1. Because you had to throw out negative 1 here. Could never divide by that 0 here. So you said x plus 1 equal to 0. So this is undefined. And so just to kind of reiterate those ideas of continuity, the function f is discontinuous at negative 1. I will say not continuous. Okay. At x is negative 1. Why? Because the limit as x goes to negative 1 of the function is not equal to the value of the function at negative 1. The limit does not exist on that left side, and the value of the function is undefined. So, ladies and gentlemen, nope, those are not the same. These are not the same ideas. Okay? Just to kind of look at that picture in the correct graph here for this. All right. This is interesting. Because now we have 3 pieces. Got 3 pieces here. Your top piece is used for values of x that are less than 0. So we call this the top. The bottom piece down here, just this x cubed, is used for values of x that are less than or equal to 0. I'm sorry, less than or equal to 1, as it says here. And then we'll say the middle piece. This is in the middle here. I will use gray. We use this for these values of x between 0 and 1, but this is x will be, 0 is less than or equal to x. So this is called the middle piece. Maybe we'll just put a little m for middle. So we have to know how to read these pieces. The graph is over here. You guys can see these graphs here. So when you're saying what's the limit as x goes to 0 from the right, you're asking to use the positive x values, because for x going to 0 from the right, meaning those values are bigger than 0. X going to 0 from the left, meaning the x values are less than 0, and they're close to 0, but they're less than them. So you got to find what piece you're going to be using for each function here. So the key again is, can you read the piecewise function? So for the first limit, as x goes to 0 from the right, they're really talking about this portion right here. Okay, and you plug in that value of x there being 0, so that'll be 3 minus 0 now. So this will be 3 minus 0, which is the value 3. And then x going to 0 from the left, meaning you have negative x values. X is less than 0. So for x being less than 0, you got to use that top piece now. That's what they're talking about now. Plug in 0 here. And so you have 4 plus 0 squared now. So it's about, can you read your piecewise function? And then do some arithmetic. So okay, the right-handed limit is 3. The left-handed limit is 4. These are not the same. So this limit does not exist at 0. So when you look at this general question, we know this does not exist. Okay, because the limits are different. Yes, they're both finite, but they're not the same. And just to see if you're awake here on this one, the value of f, the function at 0 now, you got to use the middle piece, because that middle piece says use me when x is less than or equal to 0. So you plug in 0 in that middle piece now. So that will be 3 minus 0. So this answer is just simply 3. F of 0 is 3. All right. So, I could notate it down here. And it doesn't mean much in terms of being continuous, because you're looking at what's going on around 0 here. What's going on around 0 is what you see. This is known, by the way, as a jump discontinuity. And the reason it's a jump discontinuity is because when you sketch that curve, you got to jump to get back to this point or at 0. This is where x is 0. And so that's a very much a picture of a function that's not continuous at 0. So if they ask you, is this function continuous at 0, you can say, no, f is not continuous at x equals 0, because the limit as x goes to 0 of the function is simply not the same as the value of the function at 0, because the limit does not exist. We already seen that answer right here. And the value of the function is actually 3. So this is what I want to point out to you in detail. This portion does not exist. And this portion is just 3. So this is not the same. Function's not continuous at x is 0. This is the work you do. You don't have to sketch the curve. You just have to read your piecewise function and use your definitions. Okay, it's a jump discontinuity at that location. In fact, there's another jump discontinuity. We didn't ask you at x is 1, though. You know, the left-handed limit is 2. The right-handed limit is, looks like 1. Limit does not exist. The value of the function at 1 is 1. So I can find that out just by looking at this picture here. Okay, this is a picture of, again, another jump discontinuity, but this time it's at the value x is 1. All right, pretty fun. Is it at x is 1? Yeah. So I'm going to say this. So we're going to look at this here. I'm going to change this here to be x is 1, 25, 26, 27 now. Let's look at this picture at x is 1 now. Okay. So let's do the reading of this. As x goes to 1 from the right, x is bigger than 1. And as x goes to 1 from the left, x is smaller than 1. We have to know what pieces to use just by reading that piecewise function. So this is what this means. As x goes to 1 from the right, your values of x are close to 1, but they're bigger than 1. And as x goes to 1 from the left, the values of x are close to 1, but they're smaller than 1. Okay, for x being bigger than 1 now, let's go back and read this. What piece do we use when x is greater than 1? And I can see another issue right here. That should be greater than or equal. All right, we're going to have to fix a couple of those typos on this question here. Okay, so fix that there, that typo. X is greater than or equal to 1. Now, we're going to use the bottom piece there. So this means this is going to be 1 cubed. And 1 cubed is the value 1. Now, the limit as x goes to 1 from the left, that's x is smaller than 1. And for x being smaller than 1 now, I want you guys to see it right here. This is the piece you use. So you're going to plug in 1 here for x. So that'll be 3 minus 1. Okay. Three minus 1 now is the value 2. All right. And so what we know now, again, the limit as x simply goes to 1 does not exist because these two limits are different. You know, the notation, if you wanted to see notation there, the limit as x goes to 1 from the right of the function is not the same as the limit as x goes to 1 of that function. These are not the same because 1 is not the same as the value 2. All right. But let's take a look at how to read this one again. What's the value of the function at 1? Well, the value of the function now when x is 1 is 1 cubed because we use this bottom portion for x being greater than or equal to 1. And that's going to be the value 1. Okay. And it's all illustrated in this picture. The right-handed limit is 1. The left-handed limit is 2. The value of the function, the reason they have that dot there is because you can use that portion of the curve, the x cubed, when x is 1. Because that's how it's defined here. All right. And then similarly, you can say f is not continuous, even though they never asked it in the exercise, at x equals 1. Why? because the limit as x goes to 1 of the function is not the same as f of 1, because does not exist was the limit, and f of 1 we know is the value 1, and those two ideas are not the same. That's what we're saying. All right. Okay, let's see what's going on with this question here. Remember, we got to know how to read this. The top portion of x minus 3 is used for x being less than or equal to 1. The middle portion of negative 2x squared is used for 1 between 1 and 5. Do not include 1 or 5. And then the bottom portion here is used for x being greater than or equal to 5. So we just simply have to know how to read a piecewise function. And then with the knowledge now that x is going to 1 from the right simply means those values of x are close to 1, but they're actually bigger than 1. And going to x from the left means those values of x are close to 1, but they're smaller than 1. And then that's the key to knowing what piece to use again. So x is bigger than 1, we know we got to use the middle piece. Because x is bigger than 1 is really right here. So we just simply plug in a 1 here for x, and that'll be negative 2 times 1 squared. Negative 2 times 1 squared by order of operation is negative 2 times 1, which will equal negative 2. All right. So this is the right-handed limit. It's negative 2. The left-handed limit, though, x is smaller than 1. So let's see, what piece do we use for x being smaller than 1? Oh, we use the top piece here. Because they're pretty much saying use that for x is less than or equal to 1. So I'm going to plug in 1 here for the x minus 3. So I get 1 minus 3 is also negative 2. Okay, so then that limit is going to equal negative 2 at x is, well, as x approaches 1. Because both the left-handed limit and the right-handed limit are the same. That's happening at 1. And if you look at the picture, that's definitely happening here. Left-handed limit is equal to the right-handed limit. Notice the value of the function at 1. We use the top piece, which would be 1 minus 3, which is negative 2. It's the top piece because we use the top for x being less than or equal to 1. So that says the function's continuous, ladies and gentlemen, at 1. So I'm just going to label it right here. Well, we can label it down here. F is continuous at x equals 1 because the limit as x approaches 1 of the function is the same as the value of the function at 1. In both cases, this is negative 2 equals negative 2. All right. Okay, they never asked that question, but that's what's happening around this 1 here. And now they're going to ask you another question. Hey, what's happening around 5? So if x is going to 5 from the right, we know that means the values of x are close to 5, but they're bigger than 5. And as x goes to 5 from the left, they're close to 5, but they're smaller than 5. We just have to know how to read our piecewise function and then do our direct sub. So for x being bigger than 5, go back over here. And we know, again, we got the top piece, the middle piece, and then the bottom piece. For x being bigger than 5, we got to use that piece down there because that's x is greater than or equal to 5. Use the bottom piece. So we're going to plug in 5 here. So that's going to give us the square root of 5 minus 1, the square root of 4, and that limit value is 2 when we use our direct substitution. Similarly, when x is smaller than 5, you say, what do I use when x is smaller than 5? You're going to use right here, x less than 5. So you're going to plug in 5 for x over here. And that'll be negative 2 times 5 squared now. So negative 2 times 5 squared is negative 2 times 25, which is actually negative 50. And I guess that is in the picture. That's what I was looking at. Okay. Well, the left-handed limit is not the same as the right-handed limit, so this limit does not exist. Means the limit as x goes to 5 does not exist by definition. And because of that, around 5, we know f of 5, though. You say, which piece do I use when x is 5? Well, you use the bottom piece because they say use that when x is greater than or equal to 5. So that's the square root of 5 minus 1, which would be the square root of 4, and that answer is a 2. They didn't ask this question, but be prepared for that. Our function f is not continuous at x is 5 because the limit as x goes to 5 of that function is not the same as f of 5 because does not exist is not the same as, looks like that was 2, right? Yeah. Okay. And again, you guys can look at the picture on it. The picture's fine. So that leaves us up to what we've done earlier now, before. Let's do a very similar piecewise function and call it a night here. This is x plus 1 over the absolute value of x plus 1. So I want to point out to you, we're probably going to need some paper here. Whenever you deal with the absolute value in piecewise functions, right? X plus 1 over the absolute value of x plus 1. Your denominator could never be 0. That means this whole thing can't be 0. So you have an absolute value equation to solve. And what that means is that implies that the between the absolute value sign has to be equal to 0. And solving for x by subtracting 1, we find x equals negative 1. That's the value that was thrown out of our domain. We can't have that. So x cannot be the number negative 1, just to kind of start this off. So use what we talked about in terms of the definition of a piecewise function, meaning the absolute value of anything is that thing when it's greater than or equal to 0, or it is opposite when it is less than 0. It's defined piecewise. Let's make sure there's a negative there. So when we put this together, you get x plus 1 divided by the absolute value of x plus 1. By definition is x plus 1 over x plus 1 when the x plus 1 is greater than or equal to 0. It is x plus 1 over minus x plus 1 when the x plus 1 is less than 0. And let's move this around here so you guys can see this very clearly. Now the rest is algebra because anything divided by itself is 1. Anything divided by itself where the denominator is negative, this will be negative 1. And then solving for x here by subtracting 1 now, we simply get the definition of this function is positive 1 when x is greater than or equal to negative 1. It is negative 1 when x is strictly smaller than negative 1. So this is how we get a handle on this piecewise function. Pre-calculus, ladies and gentlemen. Now remember, you said, but wait a minute, x could never be negative 1. That's right, so we have to remove the equal part. So don't forget, whenever you have piecewise, you must use these here. Got to use that definition here. And so that's really how the function's defined. It's not defined, and I want you guys to note here that the value of the function at negative 1 is undefined. It's not even defined, okay? So that means there'll be a hole in the graph at negative 1, and that's pretty much why you see what you see. This is the graph. On the top, that's the constant function 1. The bottom is the constant function negative 1. So it goes back to your graphing skills from algebra pre-calculus. So now you say, okay, let's do the limit questions. Okay, so if the limit is x goes to negative 1 from the right, means x gets close to negative 1, but x is actually larger than negative 1. You're going from the right, okay? As x goes to negative 1 from the left, you're getting close to negative 1, but these values of x are smaller than negative 1. So that's going to determine which ones we use, which piece. So for the right-handed limit now, x goes to negative 1 for the right, to the right. X is bigger than negative 1. That means we use this piece right here. The top piece. This is used when x is bigger than negative 1. That means it's 1. So it's a constant function. This is the value 1. I'll keep it orange, I guess. And then the bottom piece, you say, what do I use when x is smaller than negative 1? You're going to use that bottom piece. You say, why? Because that's how it's defined. Use negative 1 when x is smaller than negative 1. So it's going to be negative 1, the constant value. And again, what we certainly know is that these two values are not the same. So that limit does not exist. Okay? Irregardless of the approach here, this is just the limit as x goes to negative 1, does not exist. And we just got through saying that the value of the function at negative 1 is undefined. So I just want to say this function is not continuous at, very much not continuous at x is negative 1. Why? Because the limit as x goes to negative 1 of the function does not equal f of negative 1. So does not exist is not the same as saying undefined. Those are two different things. And you can actually see it in the picture. There's a jump discontinuity. When you sketch that curve, you had to jump around x is negative 1. There you go. So, we're going to maybe just do one more for fun. I apologize to you guys. One more for fun. It has the absolute value. Now, if you look at this curve, this is a nice, smooth, continuous curve. But how do we answer these questions without it? All right. Notice they gave us in this. Let's just do this one tonight, and then we'll call it a day. See that absolute value of x? because you have the absolute value of x, you want to remember to use the piecewise definition. It is x when x is greater than or equal to 0. It is opposite x when x is less than 0. That's what you're going to use. So you say, okay, 2 absolute value of x plus 7 now will be defined piecewise. It's 2x plus 7 when x is greater than or equal to 0. And then it's 2 times, let's get some space here, 2 times that minus x plus 7 when x is less than 0. So you can do a little bit of simplification of this function. The top is just 2x plus 7. That's the top curve when x is greater than or equal to 0. The bottom will be negative 2x plus 7. And you use that when x is less than 0. This is the definition of that piecewise function. Just break it into a top and bottom piece. When you see the absolute value, you want to use this definition of it. All right. So when they say, what's the limit as x goes to 0 from the right, we're talking about x values that are bigger than 0. When x goes to 0 from the left, we're talking x values that are smaller than 0. So what that might mean for us is, let's use the appropriate piece. X goes to 0 from the right. When x is greater than 0, we use this piece over here. We use the top piece. This is when x is bigger than 0, we're going to use this top piece. So just plug in 0 here for x. And you'll get 2 times 0 now, plus 7, which is the value 7. Okay. Now, for x being less than 0, you might say, well, when do I use the x being less than 0 piece? They tell you right here. You plug it in. You're going to use the bottom. So now you're going to plug in here again for x. You're going to plug in 0 like you did earlier here. You plugged in 0. But don't forget there's a negative there in front. Does it change anything? Well, not when you multiply it to 0. So this answer is also 7. So ladies and gentlemen, limit, left-handed limit's the right-handed limit, and it's 7. Okay, so the limit around 0 is the same thing. And that's really what you're seeing at this point here on the curve here. So you guys can see that. It's nice and continuous at that point. This is x is 0, y is 7, by the way. We can evaluate the function at 0 by using that top piece because it's defined for x being greater than or over here equal to 0. We didn't have to throw anything out because there's no fraction. So f of 0 is going to be 7, meaning there's no rational function. This is just nice polynomials here. And that's why if I go back over here and say, hey, guess what? F of 0 is also 7. Well, when we see this, we want to know that means the function f is nice and continuous at x equals 0, because the limit as x goes to 0, the function, is the value of the function at 0. So the key again is because you've seen the absolute value right here, use the piecewise definition of it always. And that's going to actually, give you a way to do the analysis of this. But this is how you approach this question here, ladies and gentlemen. Write it as a piecewise function. So I'm going to call it an evening and send this to you guys and correct some of those typos, and I will see you guys later. thing. I want to get to something like this, though. You see the absolute value of x minus 4? Why is this under a piecewise function? Well, yeah, because I want you guys to think of this, right? You see this function? Give you guys a fact here. It's a very useful fact. You guys want to know this. If your function that's given to you is the absolute value of anything, okay? If you guys remember from Math 260, absolute value functions are what? How do they define them? Like if I said the absolute value of, well, let's do a couple of things. Right. This is defined in terms of pieces. It's when the piece is greater than or equal to 0. It's itself. It's opposite when it is less than 0. This is the format of a what? Piecewise function. This is defined piecewise. So in the setting where they gave you, you said, what did they give us? The absolute value was x plus 4? Yeah. No, x minus 4. Okay. Doesn't matter. What you have to do is write the top piece, and you use that when x minus 4 is greater than or equal to 0. And then opposite that value when x minus 4 is less than 0. Let me write it nicer. Okay. So you must use this definition. They give this to you in pre-calculus. Okay. They define the absolute value this way. The only thing you got to remember to do is over here. Do some algebra. Meaning, if I add 4 to both sides, you're going to use this when x is greater than or what? Or equal to 4. And use this when x is less than 4. So you got a top piece again. And then you have a what? Bottom piece down here. This whole thing is the bottom piece. Okay, top and then bottom. Okay. And that's the key. You got to use the definition of the absolute value. That's key. So when they say, hey, what's the limit as x goes to 4 from the right, what do you guys know about your x values? Those are x values that are what? Greater than 4. And if you go to 4 from the left, those are x values that are what? Smaller than 4. Is that true? All right. So far, so good? So for the x values that are bigger than 4, what piece do I use? Top or bottom? For x values greater than 4, we use the what? Top. So it's going to be 4 minus 4. 4 minus 4, well, that equals 0. Do you guys know what that function is? The iPad, it does that little, drives me nuts. What about when 4 is, when looking at x less than 4, we got to use the bottom piece now, right? The bottom piece, notice, has what? The opposite sign. So that's going to be negative 4 minus 4, which is negative 0. That's really negative 1 times 0, which is 0. And that tells us the limit is actually equal to what? 0. Okay, so I know that the limit of the function is in fact 0. All right. Could you guys tell me what's the value of the function at 4 now? How do I know the value of the function at 4? Because when x equals 4, I use the what? The top piece, and that will be 4 minus 4. So I got to use the top piece, and we get 0 now. And I think this might have a typo. Yes. Let's see if we can figure it out. What did they do here? So I thought I fixed that, but maybe I didn't fix it. I might have forgotten to fix it. This is the absolute value of x minus 2 divided by x minus 2. So let's write down what this really means, okay? I'm going to need some scratch. X minus 2, I think? Okay. So the absolute value of x minus 2 over x minus 2. How do we define that? We got to take the pieces. First of all, I have to throw out the value x equals 2. Does anybody know why I have to throw that out? Because my denominator could never be what? 0. So I throw out that value of x. Okay. Now, if I start to use the definition I just gave you guys, right? I have x minus 2 over the x minus 2 when x minus 2 is greater than or equal to what? 0. And then I have the opposite of x minus 2 over x minus 2. I'm saying use that definition I just showed you guys for a piecewise function. Okay, I'm saying use this. Whenever you have the absolute value, that's what you guys want to use. So, okay, we got a top piece, we got a bottom piece. And the bottom piece is used whenever x minus 2 is strictly less than 0. I'm using that definition. So when I add 2 to both sides here and here, the top piece is when x is greater than or equal to 2. The bottom piece is when x is strictly less than 2. But I can do better. I can remember that I got to throw out what number? 2. So this never happens. Okay? But what is x minus 2 over x minus 2 equal to? This is 1, and this is negative 1. So I use this piece when x is greater than 2, and then I use this piece when x is smaller than 2. That, ladies and gentlemen, is the function in the graph. And there is a typo. You say, why is there a typo? Because your function is undefined at 2. We already said you got to throw out that 2. So what we know is the function at 2 is what? Is undefined. X could not be the number 2 because we could never divide by 0. That point is thrown out. And so this actually is an open circle. And I thought I fixed it, but maybe I didn't. When I went back and looked at it, sometimes I double task and triple task. And oh my God. Quadruple task. Oh, Jesus. Cooking dinner, texting, yelling at the dog. You guys know what I mean? Yeah. So using beginning algebra, right? Any term divided by itself is what? 1. And then this is the same thing, but there's a minus sign in front here. Okay, so that's 1. This is why we said 1 and -1. And that's why when I went back and looked at this curve, I go, oh no, there's something wrong. There's holes there. All right. So they want to know the limit as x goes to what? 2 from the right and 2 from the left. Is that right? So let me remark about this too. This is interesting. If x is going to 2 from the right, that means your x values are bigger than 2. Is that right? And if x is going to 2 from the left, the x values are smaller than 2. Okay. All right. Do you guys know something about limit of constants, by the way? The limit of a constant is that constant. If I look at the curve, this is 1, -1. As you go from 2 to the right, aren't you approaching what value? +1. And as you approach 2 from the left now, you're approaching what? -1, yes. Just on the graph. But what I'm saying is if you ever have a limit of a constant, the answer is the constant, always. So the right-handed limit is 1. The left-handed limit's -1. Ladies and gentlemen, what does this mean? The limit as x goes to 2 does not exist because the left-handed limit of the function does not equal the what? The right-handed limit of the function. -1 is not the same as +1. Going through that. So I did want to go through, this is a classic picture. It's even in your book. But there's 2 holes there. Function's not defined at 2. So I got to go back with that typo and fix that. Look at those. That's not, oh, I did want to get to, how about this one? Yeah, do we have time for this one? This is one that's in the book, actually. So I do want to talk about this function. 1 over x minus, yeah. Okay. 1 over x minus 1 over the absolute value of x. So here's something to consider. Remember I gave you that definition of the piecewise function here? See, the second you guys have the absolute value signs of functions, you want to use the pieces. Meaning, how would I define it as a piecewise function the absolute value of x? It's x when what? X is greater than or equal to 0. It's opposite x when x is less than what? 0. That's actually the definition of the absolute value function as a piecewise function. Okay? Pre-calculus gave you guys that one. All right. But in calculus, they gave you this function. And could you divide by 0? So you got to throw out what? 0. We can never divide by 0. 0 is gone just because both either location is enough to say what? Can't have that 0. But then what is the piecewise function really going to be? Yes, we throw out 0. How do we incorporate all these ideas? Well, keep what's there and now use x when x is greater than or equal to 0. Use the top and then use the bottom when x is less than 0. So keep it simple. This is really what's happening. This and this for the various pieces. This is on top, and then this is on bottom. But you know x cannot be 0, so you got to remove that can never equal 0. So remove where it's equal to 0 now. And then you simplify. You say, what do I mean by that? Well, what's 1 over x minus 1 over x? Algebraically speaking, that's what? 0. What's 1 over x minus a minus 1 over x? 2 over x. You're using some algebra. X is greater than 0. What's this? X is less than 0. This, ladies and gentlemen, is a textbook question. They gave you that function. I told you I'm leading you to where you need to where you guys need to be. And that's the function, 0 and then to the left. Okay. Now, what do they ask? What's the limit as x goes to 0 from the right? Those are values of x that are what? Bigger than 0. What about x values going to 0 from the left? So what do you guys know for x greater than 0? What's the answer? What piece do you use when x is bigger than 0? Yeah, the top piece, which is 0. Is that right? So what's the top piece? Oh, that's just 0. Okay. There we go. And then you say, well, what piece do I use as you go to 0 from the left? Well, you got to use what? The bottom piece. Now, remember what I said earlier. Curves, every B-STEM student should what? Know. You want to know that curve too. 1 over x, or even 2 over x, is this what? Hyperbola. So as x goes to 0 from the left, again, where does this function go to? Negative infinity. So notice that I didn't use a calculator. In fact, this is not really about using a calculator. If you want to jump to a calculator, you're already done. Think of all the things you're working with without using a calculator. Think of it that way. And then you're going to be on the right mindset to know, okay, I guess I got to approach it differently the way we've talked about it. And so now use the definition. What's the limit as x goes to 0, irregardless of the approach? What's that going to be? Yes. And, you're not going to have continuity at 0 at all because why? The function is not continuous at 0 or discontinuous. Why? Because the limit does not exist, by the way. And that's not equal to the value of the function. What is the value of the function? Ooh, let's see if you guys can tell me. Go back over here. What's the value of the function at 0? Nope. Undefined. Good. This is what? Undefined. Why? We had to throw 0 out, didn't we? X can't be 0. So undefined means not defined. So be careful here because I have students that think does not exist is not the same as being undefined. Okay, this is a key idea. Does not exist applies to a limit. Being undefined applies to the value of the function. Okay, we're going to work on this next question. If we look at this, we want the limit now as x goes to -5. Let me move some things out of the way over here. Limit as x goes to -5 now. Now, remember, this is a two-sided limit. We need to look at the left approach and the right approach. So you're going to -5 from both the left and the right. -5 is over here. So just looking at the picture, we know that the limit as x goes to -5 of the left of this function is going to be 0. Remember, this particular location is the coordinates of x is -5, y is 0, and your limit is the y value again. So this equals 0. Now the limit as x goes to -5 from the right of the function, the right-handed approach, this location here is x is -5, y is 2. This is where 2 is. So again, as you approach from the right side now, that limit value is 2. And since these two are not the same, we say the limit does not exist. So, okay, here's the answer to this particular question, number 52. I just want to notate a few things. Let's note that the value of the function at -5 is illustrated by the solid colored dot here. That value is 2. I'm sorry, that value is 0 over here. Again, it's that y-coordinate value. So we can say this equals 0, but we also want to notate at this particular location we have a jump discontinuity. Okay, the function is not continuous at the value x is -5. So that's kind of the exercise to some degree as to why we're looking at this and trying to find limits, is because we're going to move on eventually to the continuity questions. All right. Okay, now what's the limit as x goes to +3? Again, this is a similar question. What's happening at +3? And we'll look at this. I'm going to get rid of all the drama. We're going to change the x value now to +3. And at +3, oh, look, we got a vertical asymptote. Vertical asymptote at x equals +3. Okay. So if we look at the limit as x goes to +3 from the left of this function, we will see that that's -infinity, while the limit as x goes to +3 of the function is also -infinity. They're going down forever here at that vertical asymptote. So that means the limit here is actually -infinity. There you go. All right. Now, the limit as x goes to 6. Let's see what this is. So what's happening at 6? You have 1, 2, 3, 4, 5, and 6 now. This is where 6 is. This location. You say 1, 2, 3, 4, 5. Oh, that's also 6. It looks like this is a 6, 6. All right. So what's nice about this particular picture to make the observation that the left-handed limit will equal the right-handed limit, and they're both equal to 6. So they really want us to be able to just take a look at this and give our answers in regards to limits. Can you visually find those values there? Do you know that that function is continuous at 6, right? So this is a picture of a function being continuous at a point. We can say f is continuous at x equals 6 here. Now, if you look at the limit as x goes to -9 now of this function, one, two, three, four, five, six, 7, 8. -9 is over here. And so we go down 1, 2, 3, 4, 5, 6. That's where -7 would be. Okay, so x is -9. The y coordinate is -7. Again, it looks like this function is nice and continuous when x is -9. The left-handed limit equals the right-handed limit, and it is -7, the y coordinate value again. So this equals -7. There you go. So we answered these questions here just by looking at the general graph here. We don't really have it defined for us algebraically, but we can answer graphically what those limits are, and that's kind of the idea. And we can also notate when a function's continuous, remember? That the limit as x goes to a of the function has to be f of a. And then we can say f is continuous at x is a. So we're doing a few things here, even though we're not answering every one of those questions because they weren't asked, but just keep that in mind. We got another exercise, again, that's very similar here. Let's see if we could breeze through this, right? X goes to -7. So we got to find where -7 is. And we have 1, 2, 3, 4, 5, 6, 7. That's where -7 will be. We're at -7, comma, -1. There you go. The y coordinate value. So let's see what's happening as we approach the left side of -7. Keep in mind again, I think I'm going to color this red this time, that this open circle location is -7, comma 2. Okay? And why is that important? Well, the left-handed limit will be +2. The right-handed limit will be -1. So if I write that down, limit x goes to -7 from the left of the function is +2. The limit as x goes to -7 to the right of the function is -1. These two values are different, does not exist. So the left-handed limit doesn't equal the right-handed limit. That does not exist. Now x goes to -2, but I guess before we go there, let's kind of notate. I just want you guys to note, if you can read graphically, what's the value of the function at -7, right? Well, because we have this closed dot, the value of the function is -1. It's -1. That means to include, that point on the curve when x is -7. So this is -1. Then as x goes to -2 over here, again, we have a vertical asymptote here. This is happening at x is -2. So let me color that red. Vertical asymptote. And notice they're both going to infinity here for the vertical asymptote of x being -2. So since they're both going to the same location, this is infinity. Left-handed limit equals the right-handed limit. I'll write that down. Sometimes they'll say, please justify your answer, while the left-handed limit is equal to the right-handed limit. The function, and they're both equal to infinity. Or they're all equal to infinity. Okay, limit as x goes to 8 now. So let's try this out. Where's 8? 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Here's where 8 is. X is 8. Y is 2. So this function is nice and continuous at x is 8. So the limit as x is 8 will be 2. Okay, because as you approach from the left, those various x values from the left, you're approaching the same location in terms of the y coordinate. And, just to kind of remark, the value of the function at 8 is 2. So, they didn't ask us that, but I want you guys to keep that in mind. And there you go. So, all right. I hope you guys enjoyed the demonstration.